All right, today we are diving headfirst into one of the biggest, most fundamental ideas in all of physics. How do strings, these tiny vibrating strands of energy that might make up everything, actually talk to each other? The key to unlocking this whole thing is a seriously beautiful and, notoriously complex piece of math called the string S-matrix.
So, here's our game plan. We're going to start with how you even begin to calculate string interactions. Then we'll hit a wall, a really big one, this problem of redundancy. To get around it, we're going to look at a donut, believe it or not, a torus. That's going to lead us to this amazing idea of a map of all shapes called moduli space. And finally, we'll put all the pieces together and see how the path integral gives us the final answer.
First things first, what are we actually trying to do here? The whole point of string theory is to say the universe isn't made of little points, but of tiny vibrating strings. So probably the most basic thing we need to figure out is what happens when they run into each other? And really, it all comes down to this one question. You've got a couple of strings coming in, they interact, and maybe some new strings come out. What are the odds? What's the probability of that specific thing happening? We need some kind of tool that can actually calculate those odds for us. And that tool is the S-matrix. The best way to think about it is like a master equation, a cosmic playbook. It takes the before picture, two strings flying toward each other, and it spits out the probabilities for all the possible after pictures. Now, here's the really crucial difference. A point particle, it just traces a simple line through space-time. Easy. But a string is already a line, right? So its history, its path through time, isn't a line. It's a two-dimensional surface. Physicists call these world sheets. And the S-matrix has to somehow add up every single possible surface the strings could possibly form. Right, so you try to sum over all those surfaces and bam, you immediately hit a massive roadblock. It's this deep problem of redundancy. You end up with way too many mathematical descriptions for the exact same physical event. And when you have too many, your answer just blows up to infinity. The technique we use for this sum is called the path integral. It's an absolutely mind-blowing idea from quantum mechanics. It says that to get the right answer, you can't just consider the most likely path. No, you have to consider every single possible history that could get you from start to finish. For strings, this means we have to sum over every possible shape their world sheet could take. And this gets to the absolute heart of the problem. The math gives you an infinite number of ways to describe the exact same physical shape. It's like, imagine you're describing a basketball. You could put your coordinate system here or there, you can rotate it. You have an infinite number of mathematical descriptions, but it's still the same basketball. The path integral, if you just let it run wild, tries to count every single one of those descriptions as a different history. And that gives you infinity, which is, well, it's just wrong. So the whole game becomes figuring out how to count each unique physical shape only once. This process of getting rid of all the mathematical duplicates is called gauge fixing. And as the great string theorist Joseph Polchinski puts it here, we have to pick just one representative from each family of identical shapes. It's like we all agree that no matter how a basketball is turned, we're only going to count it as one basketball. So to really get a grip on this, let's simplify. Let's look at the easiest possible interaction for a single closed string. It just travels along for a bit and then comes back to where it started. The world sheet it carves out in spacetime has the shape of a torus, which is just the fancy mathematical name for a donut. Now, if a point particle did this, its history would just be a simple loop. And after we fix all our redundant descriptions, the only real physical thing that's left to describe it is its length. That's it, one number. But for a string, because its history is a whole 2D surface, it's a lot more complicated. You can't just describe its shape with one simple number. And this is the absolutely brilliant trick physicists use. Instead of trying to do math on a curvy donut in 3D, they just unroll it. They show that it's mathematically the same as a flat parallelogram. You just have to remember the rule. The top edge is glued to the bottom edge, and the left edge is glued to the right. If you do that, you get your torus back perfectly. This flat parallelogram is way easier to work with. So here's the kicker. Even after we've used all our mathematical freedom to fix the overall size and orientation, there's still something left over. One parameter that we just can't get rid of. It's a complex number that physicists call tau, and it describes the genuine intrinsic shape of that parallelogram. How squished it is or how skewed it is. This isn't a math artifact. It's a real physical property of the world sheet's geometry. And this leads to an incredibly powerful idea. If this one number, tau, describes the unique shape of our torus, then we can actually make a map, a complete catalog of every single possible shape a torus can have. So any parallelogram you can possibly draw, each with its own unique squish and skew, corresponds to exactly one point on this map on the right. This amazing map has a name. It's called the moduli space of the torus. So what is a moduli space? It's a geometric space where every single point represents a unique shape of some object. In our case, the object is the torus, which is a type of mathematical surface called a Riemann surface. So basically, moduli space is the perfect tool for us. It's a way of counting all the possible shapes without accidentally counting any of them twice. But wait, there's one last super subtle catch. It turns out that some parallelograms that look different can actually be cut up and re-glued to form the exact same physical torus. We're still overcounting. This shaded area you see, this is the solution. It's called the fundamental domain. Every single point inside this region represents a truly, absolutely unique torus shape, counted one time and one time only. This is our final master catalog of shapes. These modular transformations are the reason we need that special region. You can take your shape parameter, tau, and just add 1 to it. This is like shearing the parallelogram. But the torus you build from it, it's identical. Or you can do this more complicated trick, sending tau to -1 over tau. Again, same torus. The fundamental domain is specifically designed to pick just one representative from all these families of shapes that are secretly the same. Okay, so we've done it. We've managed to isolate the true physical shape parameter, tau, and we've even built a map of all its unique values. So now what? Well, this is quantum mechanics. We don't get to just pick our favorite shape. The rules say we have to consider all of them. Remember, the path integral told us to sum over all possible histories. And since the intrinsic shape of the world sheet is a critical part of its history, we have no choice. We have to sum over all possible shapes. And now, finally, we have the right tool to do that. We have to integrate our calculation over the entire moduli space, over that fundamental domain we worked so hard to identify. Now, the actual math for doing this is intense, but the logic is what's really cool. Physicists use this incredibly clever technique called the Fadeev-Popov procedure. It's like this. Imagine you did a calculation, but you accidentally counted everything 1,000,000 times over. This procedure lets you mathematically divide out that factor of 1,000,000. To make it work, you have to introduce these helper terms called ghosts. They aren't real particles, don't worry. They're just mathematical tools that exist only to make the math work out. They perfectly cancel the infinities from our overcounting and leave behind the perfect recipe, a measure, that tells us exactly how to do the final sum over our map of shapes. And this is it. This is the whole thing, the culmination of all that work. This formula is the probability for a string interaction. And look, you can see it right there, sitting inside the formula. The integral over our fundamental domain, the integral over d tau. That little piece of the equation is the solution we were after. It tells us precisely how to sum over every single possible shape of the interaction, once and only once. I mean, it's just so profound when you stop and think about it. This one single expression manages to correctly sum over all the different ways strings can interact, all the physically distinct shapes for each interaction, and all the quantum wiggles on top of those surfaces. It takes multiple kinds of infinity and tames them all to give us a single, finite, physically meaningful answer. It's incredible. And that leaves us with this really deep, almost philosophical question. The math works, and it gives us answers that make sense, but if the fundamental laws of nature really demand this kind of democratic vote over every conceivable geometry, every possible shape the universe could take on at the tiniest level, what does that tell us about the fabric of reality itself? It's definitely something to chew on.